Let's study graphene, one of the most attractive materials today. Graphene is a two-dimensional material composed of a single atomic layer of carbon atoms arranged in a hexagonal, honeycomb-like lattice. Each carbon atom in graphene is sp2 hybridized, meaning it forms three strong covalent sigma bonds with three neighboring carbon atoms. These strong sigma bonds create a highly stable and rigid in-plane structure. The remaining unhybridized p orbital on each carbon atom overlaps with neighboring p orbitals to form a delocalized pi electron system that extends across the entire graphene sheet. This delocalized pi electron cloud allows electrons to move freely within the graphene plane and is a key reason for graphene's very high electrical conductivity. In nature, graphene does not usually exist as an isolated layer. Instead, multiple graphene sheets stack together to form graphite. Within each graphene layer, the carbon-carbon bonds are very strong. However, between adjacent graphene layers, the interaction is governed by weak van der Waals forces. These weak interlayer forces are much weaker than the covalent bonds within the graphene plane. As a result, the stacked layers in graphite can be separated by supplying external energy. This separation process is known as exfoliation, in which individual graphene layers are peeled away from bulk graphite. Importantly, exfoliation breaks only the weak interlayer interactions, while the strong sp2 bonded carbon network within each graphene sheet remains intact. Graphene exhibits an extraordinary combination of properties that make it one of the most remarkable materials discovered to date. It possesses ultra-high electrical conductivity and extremely high charge carrier mobility, allowing electrons to move with minimal resistance and enabling very fast electrical response. Graphene is also exceptionally strong yet flexible, meaning it can withstand significant mechanical stress while bending without breaking. Because of its extremely large specific surface area, graphene provides abundant active sites for surface interactions, which is particularly valuable in applications such as energy storage and sensing. In addition, graphene shows outstanding thermal conductivity, allowing heat to spread rapidly and efficiently. Chemically, graphene is highly stable under many conditions, while its edges and defects can be selectively modified, offering a balance between durability and tunability. Together, these properties, high electrical and thermal conductivity, mechanical strength and flexibility, large surface area, and chemical stability, make graphene one of the most attractive materials in modern science and technology. One of the most important application areas of graphene is energy storage. Graphene is widely studied in batteries, supercapacitors, and hybrid energy storage devices, where it is typically used as a conductive additive, a composite component, or a structural framework. In these systems, graphene enhances electron transport, improves rate capability, and increases cycling stability, rather than acting as a standalone active material. Graphene is also used in thermal management materials. Owing to its very high thermal conductivity, graphene-based films and composites are applied as heat spreaders and thermal interface materials to efficiently dissipate heat in electronic devices and high-power systems. Another important application area is sensing technology. Graphene is highly sensitive to changes in its surface environment, making it suitable for gas sensors, chemical sensors, and electrochemical sensors. Even small interactions at the graphene surface can lead to measurable changes in electrical signals, enabling high sensitivity and fast response. Graphene also plays a key role in flexible and transparent electronic devices. Its high electrical conductivity, combined with optical transparency, allows it to be used in flexible circuits, transparent electrodes, and wearable electronics, where conventional rigid materials are unsuitable. In addition, graphene is explored as a corrosion-resistant layer. When used as a coating or composite component, graphene can act as a protective barrier that shields metals from environmental degradation and corrosion. Graphene is further employed as a catalyst and electrocatalyst support material. Its high surface area, excellent electrical conductivity, and chemical stability make it an effective platform for supporting catalytic nanoparticles in reactions such as oxygen reduction, hydrogen evolution, and other electrochemical processes. Environmental applications represent another growing area. Graphene-based materials are investigated for water purification, filtration, and separation membranes, where their thin structure and tunable surface chemistry enable efficient removal of pollutants, salts, and heavy metals. In the biomedical field, graphene has been explored for biosensing, drug delivery, and antibacterial coatings. Its large surface area and ability to be functionalized with biomolecules make it attractive for advanced medical and diagnostic applications, although many of these remain at the research stage. Finally, graphene is studied for optoelectronic devices, including solar cells, photodetectors, and transparent electrodes. In these applications, graphene offers a unique combination of electrical conductivity and optical transparency that is difficult to achieve with conventional materials. In summary, graphene has been explored across a wide range of applications, from energy storage and electronics to environmental and biomedical technologies. While some applications are already commercial or near commercial, others remain at the research and prototype level. Nevertheless, graphene continues to be a key material driving innovation in next-generation technologies. Thank you for watching. Subscribe for more videos.